In this tutorial, we're going to be talking about binary operations. We're going to be looking at the closure property, commutative, associative, and distributive properties. We're also going to extend and look at the identity and inverse elements. We're going to start by looking at closure property. But before we proceed, let us look at the meaning of binary operation. Binary operation is the rule guiding the combination of any two elements of a non-empty set. So giving an example of set A, which is equal to 1, 2, 3, 4, 5, and 6. Binary operation is the rule guiding the combination of any two elements of this set. In many cases, binary operation is denoted by asterisk, and you're often familiar with the common operations such as the addition, subtraction, multiplication, and division. So giving an example, if you have an operation denoted as asterisk and is defined by A asterisk of B to be equal to A plus B minus 2. So if you have to find 3 asterisk 2, this is going to be equal to, so 3 will replace A for us to have 3 plus 2 minus 2, and the answer to this is 3. So this is simply an operation asterisk which is defined by A plus B minus 2. Going back to closure property, a non-empty set S is said to be closed under a binary operation asterisk if for all AB element of S, A asterisk B is also an element of S. To illustrate this property, we are going to be looking at an imaginary set S which has elements A, B, C, D, E, and F, and looking at an operation asterisk. If we said a set is closed under an operation asterisk, it means if we select any random element of this set, take for example A asterisk B, we are going to have an answer which is also an element of S. On a more general note, the set Z of all integers is closed under addition, subtraction, and multiplication, but not under division. If we set Z, which is the set of all integers, it ranges from negative to 0 and to positive. So looking at operation addition, if you take any two random elements of ZZ, which is the set of all integers, let's take 1 plus 2, we have our answer to be 3, and 3 is also an element of Z. So if you take any two random elements of ZZ and add them, we are going to have another answer which is also an element of ZZ. So we said ZZ is closed under the operation addition. So for negative, if we select any two elements such as 4 minus 5, we have our answer to be minus 1. Since minus 1 is also part of ZZ, so the same thing, if you take any two elements of ZZ and perform operation minus on them, you are going to have another element which is also an element of ZZ. So we also say ZZ is closed under the operation negative, which is minus. For multiplication, if you take any two random elements of ZZ and multiply them, for example 3 multiplied by 4, we have an answer which is equal to 12, and 12 is also an element of ZZ. So if you take any random element of ZZ, we are going to have an answer which is also an element of ZZ. So we said ZZ is closed under the operation multiplication too. Now looking at division, if you take any two elements of ZZ, here I'm going to take 4 divided by 2. Here we have 2, which is also an element of ZZ. But what if we take 2 divided by 4? We have 0.5, which is not an element of ZZ. So since we have an exception, we said the element of the set Z is not closed under operation division. Here we have an example. Operation asterisk is defined on the set M to be equal to 0, 1, 2, 3, 4, and 5 by x asterisk y to be equal to x plus y minus xy. Find A 2 asterisk 6, B 0 asterisk 3. Let's go back to our definition. The operation asterisk is defined as x asterisk y to be equal to x plus y minus xy. So in A here, we have to find the solution to the question 2 asterisk 6. Going back to our definition, x asterisk y is being defined as x plus y minus xy. So we simply replace x with 2 and y with 6. So we now have 2 asterisk 6 to be equal to 2 plus 6 minus 2 times 6. And we have 8 minus 12. Here we have minus 4. So the second part, which is B 0 asterisk 3. Still following the same definition, you have x asterisk y to be equal to x plus y minus xy. So we now have 0 asterisk 3, which is equal to 0 plus 3 minus 0 multiplied by 3. And then we have 3 minus 0 is equal to 0. Now, if you are to relate this to closure property, we have our set M, which is defined as M to be equal to 0, 1, 2, 3, 4, and 5. But we have the solution to question A, which is equal to minus 4. If you check, minus 4 is not an element of this set. So we can say that set M is not closed under the operation asterisk, since we have an answer which is not an element of this set. In looking at closure property, we can directly jump into conclusion that a particular set is closed under a particular operation if we haven't tested for all the elements of the set. Take for example, we have a set M here which is defined by M to be equal to 0, 1, 2, and 3. And the set is being defined on the operation asterisk, which is defined as x asterisk y to be equal to x plus 2y. If we take any two random elements of set M, for example, here we are taking 0 and 1. So we have our answer to be equal to x plus 2 times 1. X here is 0, and then we have our answer to be 2. Even though 2 is an element of this set, we can directly jump that set M is closed under operation asterisk. The best way to approach this is to use a operational table. We are going to use an operational table. So we have to draw our table which has the operation we are considering, which is asterisk. So we now take note of each element of this set. So here we have 0, 1, 2, and 3. The same thing we should have here 0, 1, 2, and 3. So we have to look at every element of this set and compare them with each other. So if you have 0 asterisk 0, the answer is going to be 0. So feel free to work this out and fill the whole box. I'm going to fill this right now. Here we have 2, we have 4 here, and we have 6 here. If you have 1 asterisk 0, we are going to have 1 here, 3, 5, and 7. Here we are going to have 2, 4, 6, 8. And over here we are going to have 3, 5, 7, and 9. So if you look at all the answers we have here, 0 ranges from 0 to 9. And we'll look back to the elements of set M, we have 0 to 3. So we can see that we have an answer here. For example, 9, 8, 7, 6, 5, 4. All these are not an element of set M. So we can confirm now that set M is not closed under the operation asterisk. The second property we are going to be looking at is the commutative property. Given a non-empty set S which is closed under a binary operation asterisk, if for all A, B element of S and A asterisk B is equal to B asterisk A, then the operation asterisk is said to be commutative on S. To illustrate this, let's look at imaginary set M which has elements A, B, C, D, E and F, and we have an operation asterisk here. Now if for all A asterisk B is also equal to B asterisk A, then we can say that the operation asterisk is commutative under the set. On a more general note, for example, on the set of real numbers, the operation addition and multiplication are commutative. This can be illustrated below. If you have A plus B, it's also the same as B plus A. So take for example, if you have 1 plus 2, it's also the same as 2 plus 1, and this equals to 3. So we can say that the operation addition is commutative under the set of all real numbers. What we are doing here is to simply if you can interchange. For multiplication, if you have A multiplied by B, it's also the same as B multiplied by A. So to illustrate this, if you have something like 2 multiplied by 3, it's also the same as 3 multiplied by 2, which gives us 6. But looking at subtraction, for example, A multiplied by B, that's A negative of B, A minus B is not equal to B minus A. Take for example, if you have 2 minus 3, this equals to minus 1, and 3 minus 2 equals to 1. So since this answer they are not the same, we can say that the operation negative is not commutative under the set of all real numbers. We have an example here. On the set of real numbers, an operation asterisk is defined by A asterisk B to be equal to A plus B plus 4AB. Show whether the operation asterisk is commutative. So we have our definition of the operation here to be equal to A asterisk B, which is defined as A plus B plus 4AB. What we are trying to prove in commutative law is that if we can interchange A asterisk B to be the same as B asterisk A, then we can say that the operation is commutative. And here we have A asterisk B is defined as A plus B plus 4AB. So if you can bring A, B asterisk A, this is going to give us, so now B will now replace A and A will replace B. We have B plus A plus 4BA. So we have to check whether this and this, they are the same. Under the operation addition, just like the one we have here, A plus B is the same as B plus A. And under the operation multiplication, just like what we have here, BA is the same as AB. So we can interchange this answer to be equal to A plus B plus 4AB. If you look at this very well, we are going to say that the answer to A asterisk B is the same as the answer to B asterisk A. Therefore, we can say that the operation asterisk is commutative under the set of real numbers. Let's look at another example. On the set of real numbers R, an operation asterisk is defined by A asterisk B to be equal to A minus B plus 4AB. Show whether the operation asterisk is commutative. Here also we have our operation A asterisk B, which is defined as A minus B plus 4 AB. So we are going to interchange this. I have B asterisk A, and this is going to give us B minus A plus 4 AB. So you have to check whether this and this are equal. Now we have an operation here which is negative. Here we have A minus B, and here you have B minus A. We already talked about it that under the operation minus, negative is not commutative. Under the set of real numbers, negative is not commutative. So therefore A minus B is not equal to B minus A. So here we can see that since A minus B plus 4 AB is not equal to B minus A plus 4 AB, so the operation asterisk for this example is not commutative under the set of real numbers. I'm going to leave you with an exercise here. If you have an operation asterisk which is defined as A asterisk B to be equal to 2A plus 2B, check whether the operation asterisk is commutative. Also the second one, this is the first one, the second one, operation asterisk here is defined as 2A minus B. So check whether the operation asterisk is commutative under the set of real numbers. The third property we are considering is the associative property. Given a non-empty set S which is closed under a binary operation asterisk, if for all A, B, C element of S and A asterisk B asterisk C equal to A asterisk B asterisk C, then the binary operation is said to be associative. Here we need to take note of the statement of this law. We have brackets here and we have the brackets here. Over here the bracket is inserted between A and B, and here between C and D, between B and C. Here the bracket signifies the order of the operation. So here if we consider A asterisk B first, here you have to consider B asterisk C first. We are going to consider a more general note to illustrate this. For example, on the set of real numbers, the operation addition and multiplication are associative. This can be illustrated as follows. Under the operation addition, if you have A plus B bracket plus C, this is also going to give us A plus B plus C. So we are going to have the same answer. If we insert numbers here to have something like 1 plus 2 plus 3, here we are going to have 1 plus 2 which is 3 plus 3, this is 6, and we check it with 1 plus 2 plus 3. Here we are going to have 1 plus 2 plus 3 is 5, which is also 6. So we can say that under addition of real numbers, the operation addition is associative. Also under multiplication, if you have A times B times C, it must be equal to A times B times C. For example 2, if you have 1 times 2 times 3, this is also equal to 1 times 2 times 3, and we have everything to be equal to 6 also. So but looking at subtraction, if you have A minus B minus C, this is not equal to A minus B minus C. So take for example, if you have 3 minus 2 minus 1, this is going to give us 3 minus 2 is 1 minus 1. This is going to give us 0. And if you have 3 minus 2 minus 1, this is 3 minus 1, and this is going to give us 2. So since 0 and 2, they are not the same, we can say that subtraction is not associative under the set of real numbers. We have an example here. The operation asterisk is defined in the set of real numbers R by A asterisk B to be equal to A plus 2B. Show whether the operation is associative. So here you have to input a third element C so as to check for the condition. So you have to look at A asterisk B asterisk C when that is equal to A asterisk B asterisk C. Let's split these two operation by writing this A asterisk B asterisk C here and putting the other one A asterisk B asterisk C over here. So for the moment, let's ignore asterisk C and look at A asterisk B. So our set is defined as A asterisk B to be equal to A plus 2B. So going back here, we have A asterisk B to be equal to A plus 2B. So let's bring back our asterisk C. We have asterisk C. So we need to look at this again. A asterisk B, A plus 2B asterisk C. A now stands for A plus 2B and B signifies C. So this gives us A plus 2B. This is now our A plus 2B, which is 2C. So here we have A plus 2B plus 2C. What happened here might look a little bit confusing. What simply happens is that we refer back to our operation, which is A asterisk B to be equal to A plus 2B. And here we have A plus 2B asterisk C. So we now refer to this as A and this as B. So we now have our A now is now A plus 2B, A plus 2B plus 2B. Our B now is now C plus 2C. So that is why we have A plus 2B plus 2C. So let's remove this. So looking at the other part of the equation, we have A asterisk B plus A asterisk B asterisk C. So we firstly have to consider B asterisk A. We have B asterisk C to be equal to B plus 2C. So looking at the other part of the equation, which is A asterisk B plus 2C. Now, in relating this with our definition, we now have A as our A and this as B. So this now equals to A plus 2. Since everything here is B, 2B plus 2C. So we have the answer here to be A plus 2B plus 4C. So we have A plus 2B plus 4C. If you relate these two answers, here we have A plus 2B plus 2C, and here we have A plus 2B plus 4C. You can see that they are not equal. So the operation asterisk is not commutative under the set of real numbers. It's not associative under the set of real numbers. We have a second example here. The operation asterisk is defined on the set of real numbers by A asterisk B to be equal to A plus B minus 1. show whether the operation is associative. So we have to insert another element, which is C, to check. So we have to check for A asterisk B asterisk C equal to A asterisk B asterisk C. We are going to be looking at the two conditions independently. So we have here A asterisk B asterisk C, and here we have A asterisk B asterisk C. And let's refer back to our operation, which is being defined as A asterisk B equal to A plus B minus 1. So far here we firstly look at A asterisk B. So here A asterisk B equal to A plus B minus 1. So we now look at A plus B minus 1 asterisk C. So now here this is our A and this is our B. Operation is being defined as A plus B minus 1. So we have the solution here to be A plus B minus 1 asterisk C, which is equal to A plus B minus 1. This is our A plus B, which is C minus 1. Everything here equals to A plus B plus C minus 2. So looking at the other part of the equation, we have A asterisk bracket B asterisk C. So firstly we look at B asterisk C. Here we have B asterisk C to be equal to B plus C minus 1. So now we have to look at A asterisk B plus C minus 1. And this will give us, this now our A and this B. So we now have A plus B plus C minus 1 minus 1. So we have the solution here to be A plus B plus C minus 2. So comparing these two answers, we can see that A plus B plus C minus 2 and A plus B plus C minus 2, they are equal. So we can now say under the set of real numbers, the operation asterisk is associative. Sometimes there will be need to consider two different operations on a set. In distributive law, if for all A, B, C element of S and A asterisk B, we have another operation here. For the sake of this tutorial, I'm going to be calling this triangle. So if you have A asterisk B triangle C equal to A asterisk B triangle A asterisk C, then the operation asterisk is said to be left distributive over triangle. If B triangle C asterisk A equals to B asterisk A triangle C asterisk A, then the operation asterisk is said to be right distributive. To better illustrate this property, we are going to be looking at the operation addition and multiplication. Under multiplication, if you have 1 times 2 plus 3, so here we can say this also equals to 1 times 2 plus 1 times 3. Coming back here, if you have 1 times 2 plus 3, it's also the same as 1 times 2 plus 1 times 3. So it satisfies this condition, and then we can say that multiplication is distributive over addition. But if you have something like 1 plus 2 times 3, we can say this is 1 plus 2 times 1 plus 3. So therefore addition is not distributive over multiplication. For the scope of this class, we are not going to be laying emphasis on right distributive and left distributive. We are simply going to be taking a look at distributive properties generally. Here we have an example. Operation asterisk and triangle are defined on the set of natural numbers by a asterisk b equals to ab and a asterisk a triangle b equals to a divided by b. Check whether the first one, asterisk, is distributive over triangle. Second one, triangle is distributive over asterisk. Just like what we did for associative property, we are going to insert another element C here. So here we have to check the first one, A asterisk B triangle C. Check whether this is equal to A asterisk B triangle A asterisk C. So we have to check for this condition. So first and foremost, we are going to look for the answer to A asterisk B triangle C. So here we have B triangle C to be equal to B over C, and we have A asterisk B to be equal to AB. So here we have A multiplied by B over C, and here we have AB over C. So this is the answer to A asterisk B triangle C. Now checking for this condition, so let's look for A asterisk B, and this is equal to A B. We also look for A asterisk C, which is this, and this equals to A C. So looking for this triangle, this, we have the operation is being defined as A triangle B to be equal to A over B. So we now have this now as our A and this as our B. So A asterisk B triangle A asterisk C is going to be equal to AB over AC. This will cancel out, and here we have B over C. So looking at the answer we have here, which is AB over C, and we have B over C here, we can say that operation asterisk is not distributive over triangle. So if and only if we have the same answer here, we can say that operation asterisk is distributive over triangle. The second one is to check whether triangle is distributive over asterisk. I'm going to leave this with you. Try it. Feel free to comment the answer below, and I'm going to reply to you as soon as possible. The next property we are going to be looking at is the identity element. For a non-empty set S, if there exists an element in which A asterisk A equal to A asterisk A, and this answer is equal to A, then the element A is referred to as the identity element. To better illustrate this, we are going to use the addition and the operation multiplication. Under the operation addition, if you have A plus 0, it's also the same as 0 plus A, and answer is still A. So for example, if you have 5 plus 0, it's the same as 0 plus 5, and the answer is still what? 5. Under multiplication, if you have A times 1, it's the same as 1 times A, it's also A. And if you illustrate this by using 5 times 1, it's the same as 1 times 5, and this is what? 5. So under the operation addition, we have 0 to be the identity element, and under operation multiplication, we have 1 to be the identity element. If there exists an element E in which A times E asterisk A is the same thing as E asterisk A, and the answer here is still A, then we refer to E as the identity element. Looking at this example, we have the question which says that the operation asterisk is defined on the set of rational numbers q by a plus b equals to a plus b minus 2. Find the identity element. So here you have to look at our definition, which is a asterisk b to be equal to a plus b minus 2. For identity elements, we have to get a condition in which a asterisk a is the same thing as a asterisk a and equal to a. Therefore, if you have a asterisk e here, we are going to have a plus e minus 2 and must be equal to a. So here we have a plus e minus 2 equal to a, and we have e to be equal to a minus a plus 2, and we have e equals to 2. So under this operation, the identity element here we have is 2. Now if you look closely at the definition for identity element here, we can see that a asterisk e must also be equal to e asterisk a. So here we check for a asterisk e. It's greatly advisable to also check for e asterisk a. So here if you have e asterisk a, which must also be equal to a. So here we have e plus a minus 2 equal to what? A. And we have here also that a equal to a minus a plus 2, and we have a to be equal to 2. So these two answers, they agree, so we have our e to be 2 in both cases. So therefore we can say that 2 is the identity element for this operation. The last property we are going to be looking at is the inverse element. The inverse element is greatly related with the identity element. Given a closed non-empty set S on operation asterisk, if there exists an element a prime element of S such that a asterisk of a prime is equal to a asterisk a equals to e, where is the identity element, then a prime is referred to as the inverse element. To better illustrate this, we talk about the identity element of positive to be equal to 0 and the identity element of multiplication to be equal to 1. If you have a number such that a multiplied by a prime to be equal to e, then we refer to a prime as the inverse element. For example, if you have an element a multiplied by a prime and this is equal to e, which is the identity element under multiplication, and that is 1. So looking for a prime here, we have a prime to be equal to 1 over a. So then we refer to 1 over a as the identity element, or as the inverse element of multiplication. And for addition, if you have a condition whereby a plus a prime equals to e, here we have our e to be equal to 0. So here we have a plus a prime equal to 0, and here we have a prime equals to minus a. So it refers to minus a as the inverse element of addition. In inverse elements, the condition we are supposed to satisfy is that a asterisk a prime must be equal to e. So if you look at operation multiplication here, and we take number as 5, so if you multiply 5 by a prime, and a prime here is 1 over a, which is 1 over 5, you must get 1, which is the identity element. So the same thing here, if you have 5 plus a prime, which is minus a, and this is equal to 5 minus 5, and the answer is 0. So this is the concept behind inverse elements. Most often inverse is denoted as a raised to the power of minus 1. This is only the case whenever we are considering the operation multiplication. Looking at this example, we have the operation asterisk is defined on the set of real numbers out by a asterisk b equals to a plus b plus 1. Find the inverse of a. Before we can get the inverse, we have to look for the identity element. And to get the identity element, we have a asterisk a must be equal to a asterisk a must be equal to a. So considering a asterisk e, we have a plus e plus 1 when we relate this with the definition for the operation. So the same thing if you have e asterisk a and this equals to e plus a plus 1, and since these two they are equal, we can equate this to a. We now have e plus a plus 1 equal to a, and we have e equal to minus 1. So in looking for the inverse of a, we have to satisfy a condition in which a asterisk a prime equal to e, and since we already have our e to be equal to minus 1, we now have a asterisk a prime equal to minus 1, and a asterisk a prime is defined as a plus b plus 1. This is the definition for our operation. So a asterisk a prime here will now be equal to a plus a prime plus 1, and this must be equal to minus 1. So here we have a prime to be equal to minus 1 minus 1 minus a, and we have a prime equals to minus 2 minus a. So here we have our inverse element to be equal to minus 2 minus a. In summary, in this tutorial we have talked about the closure property, the commutative property, the associative property, the distributive property, the identity element, and the inverse element. So congratulations, we have come to the end of this tutorial. We have 2 exercises here. I want you to try them out. If you have any challenge in solving them, feel free to comment below and I'm going to get back to you. If you like this tutorial, like, share, and don't forget to subscribe for more simplified solutions such as this.